Hi, my name is João Vignoli, and I'm going to present our work, CNN-based change detection algorithm for wavelength-resolution SAR images. We are with the Federal University of Santa Catarina, the Aeronautics Institute of Technology, and the Blackfinch Institute of Technology. The synthetic Aperture radar. It is an airborne or orbital pulsing radar. It measures the intensities and phases of the reflected pulses, like any other radar would do. But it has a virtual aperture, which leads to a high azimuth resolution. And it is independent of weather conditions, which makes it a good choice for many applications. Here's an example of a SAR image, another example, and another example. In this example, showing the Pentagon in Washington. And change detection in SAR images is an important application of SAR images. It is used to detect changes in SAR images from the same scene at different instants of time. For example, it is used in defense applications, deforestation monitoring, urban planning, and ocean monitoring. And usually it is performed by Bayesian methods or classic signal processing algorithms. And most change detection algorithms require two SAR images. One is the reference image and the monitored image. The monitored image is the image of interest that in which we want to analyze and discover whether there are any changes present in this image in comparison with the reference image. Here's an example of a SAR change detection. The difference image is the last one. And wavelength-resolution SAR, it is a class of SAR radars that operate in low frequencies and generate illuminations that are free from speckle noise, which is usually a multiplicative noise present in high frequency SAR images. And the resolutions of the illuminations are in the order of the wavelength of the transmitted pulses. And for this reason, it achieves maximum resolution. Also, small scatterers are ignored, such as leaves and little rocks, small objects in general. And it produces illuminations that are unstable in time. And the Carabas-2 dataset is a dataset that consists of 24 incoherent wavelength-resolution SAR images with targets concealed by foliage, dense foliage. And so these images contain 25 military vehicles spread through an area in Sweden and are concealed under dense vegetation, and were made available in a challenge problem. After it was made available, many change detection algorithms have been developed. Examples of the Carabas-2 dataset. Here we can see the vehicles concealed under foliage, those dots, and the overview of the algorithm. We propose a CNN-based change detection algorithm for wavelength resolution SAR images. And the Carabas-2 dataset was adopted as the training and testing dataset. First step we do pre-processing. Reference image is subtracted from the monitored image, which generates a difference image, and it is then normalized to have zero mean and unit variance. Then it is fed to a semantic segmentation CNN, which will analyze this difference image and localize pixels that are possibly parts of changes. In the end, a decision threshold omega-1 is applied, resulting in a binary image, which indicates which pixels are most likely to be part of changes. Next, we do a clustering, and it will search for clusters of positive elements in the binary mask that was generated before, and finds these clusters and determine the central points of them. And finally, the classification. Small patches around the center of possible changes that were found by the clustering algorithm are fed to a second CNN, which will analyze further whether each one of these patches contain a target, contain a change or not. Let's now visualize how the algorithm works. The monitoring image and the reference image are combined to produce the difference image. It is fed to the segmentation CNN, which will spit out a probability map representing which pixels are most likely to be part of changes. And the DBSCAN algorithm receives a binary mask that was thresholded by omega-1 and localized these possible changes, which are the bright spots in this image, and gives the central coordinates of these possible changes to the classification CNN, which will analyze each one of the patches around the centers of possible changes and determine whether they are changes or they aren't changes. The train test.split, we had a problem because the curvature dataset had only 24 SAR images, and we could not separate even more this small dataset. We had to come up with a solution to use all 24 images for both test and training. We have used the k-fold cross validation and separated the dataset into 6 groups called folds, such that for each fold was either the test set or train set, and 6 variations of these selections could be performed, such that for each split, one subset was a test set and the other 5 subsets were the train set. In the end, all 24 images were used as both test and train, for both testing and training. Here is the distribution of images, and here are the details of the proposed CDA. Here is the difference image. It is then analyzed by the segmentation network, which will spit out this probability map indicating which pixels, the probability of each pixel being part of a change, which is then threshold by omega 1, which will select those pixels that are most likely to be parts of changes, producing a binary map. Here's the segmentation CNN description. Here is the DBSCAN. The DBSCAN will receive the binary mask and find where are these clusters of pixels of possible parts of changes and determine the central coordinates of each one of these clusters. These clusters localized are then cut and sent to the classification network, which will analyze patch by patch around the center of clusters and determine whether each one of these patches are changes or are clutter. In green we can see the true positives that were detected, the false negatives that were not detected, and one false alarm here in hat. The classification model description, the training. The input of the segmentation training, the segmentation network. The segmentation network was trained using the difference images of 3000 by 2000 pixels, in which and the ground truth was selected as binary masks containing ones where targets were positioned, so that for each target for each vehicle in these images, a square L1 submatrix of 3 by 3 or 5 by 5 was inserted into the binary mask, so that each non-zero element in this mask represented a pixel of a target. Other non-target pixels are represented as zeros. And the classification ground truth, a sliding window approach, we cut the 24 SAR images, SAR difference images, into sub-images of 34 by 34 pixels with a 10 pixels overlap. In the end, we had more than 10 to the 4th negative sub-images, because the sub-images with targets were discarded, and the value of y equals 0 is associated to each sub-image. And the sub-images containing a target. For the sub-image containing a target, we cut a sub-images of 34 by 34 centralized on the central coordinates of targets, such that in the end we had 25 positive sub-images from each difference image, and the value of y equals 1 is associated to each sub-image. And the data augmentation took place because we had few positive examples, and we wanted to increase the number of positive, and we wanted to increase this number. So each positive subimage has been duplicated and rotated in 90 degrees clockwise, and in the end we added Gaussian noise with variance 100 and 0 mean. Following, the same transformations were performed in the negative examples, but without duplication. They were performed in the examples directly, with a probability of 0.7. And here is the focal loss balanced cross entropy function that was used to train the models, because this loss function has been proven to increase performance and reduce training time for highly unbalanced datasets like ours. Here are the parameters of the loss function, the parameters of training, and the obtained results. In the metrics of comparison are the probability of detection, which is the system recall, and the false alarm rate, which is the ratio of the number of false alarms by the area under surveillance, which in this case is 6 km² for every image. and the performance is presented in terms of a ROC curve. Firstly, the performance of the proposed CDA without the classification, the final classification is presented, so that the output in this case are the DBSCAN predictions. The points of operation of this ROC curve are obtained by varying omega-1, and we can notice that the CDA has surpassed the state-of-the-art in the performance for far bigger than 0.174 per kilometer squared. Here is the curve. Our algorithm is the purple curve. And a complete CDA we can evaluate by choosing different operation points and by a pair omega-1 omega-2, so that many ROC curves can be obtained by choosing omega-1, while we vary omega-2. And an adequate choice of omega-1 needed to be done, because many ROC curves were defined by different choices of omega-1 and were generated in the CDA's development phase, folds from 0 to 4, such that the last fold was not used to develop their algorithm. It was reserved for the final test. And the range of values for omega-2 has been fixed for every curve for a fair comparison. And the segmentation threshold of 0.68 has yielded the biggest AUC for far less than 0.8 per kilometer squared. Here is the value 0.68, the biggest AUC in function of omega-1. Letting omega-1 equals to 0.68, the final evaluations were performed, and we can see that our algorithm here in blue has outperformed all other state-of-the-art CDAs. The performance per fold was consistent, which is a sign that the models didn't overfit to the images used to develop them, because the fold 5 has been reserved for the final test. It wasn't used to develop their algorithm, so we can see that it has presented an excellent performance, which is a good sign of non-overfitting to the images used to develop the model. Here is a comparison with a point of operation and other algorithms, and the number of images used for each prediction. We can see our CDA can outperform other algorithms, even that ones which use more than 2 images per prediction. And a possible limitation is that the classification network has been trained with a limited number of examples of changes. So in the end, if you want to detect changes whose morphological attributes are much different from those of the changes present in the dataset Carabas 2, we would have to retrain the models with more representative examples, of course, like every other neural network would require. Thank you very much for your time. I hope I made myself clear.